Alright, cool. So last time we were looking at uniform circular motion, where we looked at some of these. We talked about centripetal acceleration. So we're looking at rotation angle, where you have a theta, the change in theta, and then the delta S on the outside, the change of motion along the outside divided by R. So then you have a radius, of course, so that looks a little bit like this. So as it spins, A to B is called delta S, which is the same as the displacement or revolutions. It's called the arc length. The arc length is the distance traveled along a circular path. Note that R is the radius of curvature of the circular path. So and then we have theta. So that equation, d theta equals ds over R. So now as we look at ds, okay, what is that? Well, that would be the 2 pi r, because it says we know that for one complete revolution, the arc length is the circumference of a circle of radius r. The circumference of a circle is 2 pi r. Thus, for one complete revolution, the rotation angle is 2 pi r. So now we're looking at radians. 2 pi radians equals 1 revolution. So now we're looking at the radians. We know 90 degrees, pi over 2. Well, starting at 180, you know 180 degrees is pi. So then you could go down from there a little bit easier. You say, oh, 3/4 of pi, 2/3 of pi, half a pi, third of pi, 6 of pi. You know, so and then 360 must be 2 pi. So then we're looking at angular velocity. Angular velocity is d theta over dt. So then looking at linear velocity, ds over dt, change in s over the change in time. So then we have our relationship between angular velocity and r. Angular velocity equals v over r, or v equals r omega. Where we can see this in a car tire. Calculate the angular velocity of a 3.3 meter radius car tire when the car travels 15 meters per second. So and then we're looking at omega equals v over r to calculate angular velocity. So we have our velocity of the car, and then also the r, the radius of the tire. And that's all we need to know for angular velocity. So then it's saying, also note that if an earth mover with much larger tires, say 1.2 meters in radius, were moving at the same speed, its tires would rotate more slowly. They would have an angular velocity 12 radians per second. It's pretty interesting. So this is the experiment. Tie an object to the end of a string and swing it around in a horizontal circle above your head. Swing at your wrist. Maintain uniform speed as the object swings and measure the angular velocity of the motion. What is the approximate speed of the object? Identify a point close to your hand and take appropriate measurements to calculate the linear speed at this point. Identify the circular motions and measure their angular velocities. So we can actually do this. see if we have a time. You have your stopwatch on your phone or something?
Yeah.
So I brought this in to mimic swinging. So we have uniform circular motion here, you know. So one thing going on, you have like tension, pulling, so and then we start learning about centripetal acceleration. So centripetal acceleration wants to keep it attached to the motion. It keeps it going toward the center. So if I'm going toward the center, then I'm constantly gonna be angling my curvature going toward the center. But then we also have Coriolis force. So when we learn about Coriolis force, we learn centrifugal force, which is the opposite of centripetal force. So we were talking about centrifuge last class too. So we were talking about the spinning, and then we were able to see, so centrifuges spin around and around and push the particles apart. So the Coriolis, or really centrifugal force, will be able to push this. It wants to push it away. So if I were to let go of this, then it'll go in a straight direction. It'll go directly out, away from the center of Earth, of course, like the center of the object, because it constantly has a velocity going outward as well. So, or perpendicular to, but it wants to push outward. Centripetal acceleration wants to keep it in. And you have uniform circular motion as we spin. So that happens. You also have the angles. So we know, here's 90 degrees from that point. Here's 180. So we have our radians as well. We have a radius. So we could say from this point to this point, we have our pi over 2. And then from here we have pi. So, and then we start learning about centripetal acceleration. So I wanted to see the speed. So we talked about all that. I wanted to see the speed that I might be rotating this right here. So omega. So we get that from omega. R d theta. So V is R omega. So omega equals V over R. Looking for my, here we are. Over the change in time. So here we are. Our d theta over dt. So how fast is this object rotating? So I'm thinking that what we could do is try to get from this point right here and try to see what it looks like as a full revolution. So I'm thinking if I'm rotating in like a normal, a harmonic oscillation, uniform circular motion, and we can say boom, boom, kind of like start, stop, start, stop, do something real fast, or it might be kind of fast, but we could try to say like, okay, start, stop,
Yeah.
So that's the goal that I'm thinking we can accomplish. So it is moving at uniform circular motion. So I'm thinking, you know, I like, you know, you could choose whichever spot you want to go to, but I like looking at it like it's the same pie chart that we always know and love, where 0 is over here and then 2 pi goes over here again. Yeah. So that's what I'm hoping we can do, and then we'll have our changing theta over changing time, and then velocity, the changing s, where we can add in the radius of this object, because we have velocity and then we also have acceleration. So our acceleration will change because that is the change in velocity. So we have an angular velocity, and then we should be able to find out the change in the acceleration, what it is as well. All right, cool. Let's try it out.
So you gonna tell me when to start and stop?
Yeah.
Okay.
Yeah, it'll be real quick.
All right.
All right, you ready? And start, stop.
Okay. 0.82.
All right, 0.82. All right, so for 0.82, and you get individual study today. Yeah. Omega. I know it's also the change in seasons, so I know some people are getting sick. So my change is 2 pi. And you said 0.82 seconds. So this is pretty simple. Two pi. I found out something. I was researching about those radians and degrees. 7.66. So 2 pi equals 1 revolution. This would be revolution per second. One thing that you might have seen before is RPM in a car, rate per minute. So that's very similar, you know, as I'm moving, as our engine is moving, we have a rate that our engine's moving, and you know, as it's going, you got to make sure that your transmission is going in good spots, because that's going to help you propel, because the engine is going to be moving, oscillating, and as I have my RPMs go up, I need to go ahead and move it to the next gear. You know, as I'm in that gear, I'm moving faster, and then my RPM goes up, I gotta change it to the next gear. So it's we look at RPM more in manual shift cars, you know, as opposed to automatic. Yeah. You know, we don't really talk about RPMs too much anymore. because we don't really need it. We just press gas and
Yeah.
it goes. But I actually have another car, the Honda Civic, and it's a stick shift.
Okay.
So I actually look at RPM. So that's something that I saw that was pretty interesting. So this should be our angular velocity. So and then should be able to get my V. So that's angular velocity. The linear velocity is there. So now I can see my linear velocity. V equals R omega. So and then R omega is gonna have to give me my radius, which now I need the radius for my string to object. So I see this is already in inches. Yeah, so these are centimeters. So I see 44, which is 0.44 meters. 0.44 meters times my omega. 7.66 revolution per second. So then I should have my linear velocity. 0.44 times 7.66. Oh, I forgot to bring up what before I get to that, one thing, the revolutions or radians are, they say that they're unitless, that we don't trying to see how to explain that we don't, they say that is unitless, but so when we put in our radius and our angular velocity, find our linear velocity, so and then all I need to do is put meters to seconds, which makes sense. You know, velocity is meter per second. So then this is our linear velocity. The reason why is this right here. So since we have, because our angular velocity we'll want to keep in, but then a linear velocity at that point, like I was saying, it's gonna be facing outward. It's gonna be facing perpendicular to our line of motion. So that's why we have a linear velocity as well. Because I have a velocity keeping me on the path of that angle, so that's angular velocity. And then I also have a linear velocity. And then look at centripetal acceleration. So here's centripetal acceleration. Equals so because V and R are given the first expression, AC equals V squared over R is the most convenient to use, which is also AC equals R omega squared. So we could do either one, but we just found out for V, so let's try V squared over R. So and then we have 3.3 meter per second over radius. Oh, that's why it's squared. Radius 0.44 meters. Squared. Divided by 25.8, and they should give me a percent squared. But I have the squared of a meter, cancel that out, meter, and then I have a second up here. So now I have meter per second squared.
So what does that W mean
Angular velocity. And that is omega. That is lowercase omega.
again?
Uppercase omega, like that. Lowercase omega is like that.
Oh, okay.
Yeah.
And then you said the centripetal acceleration, that is the force inward.
Mm-hmm. Mm-hmm. Which means that it's also the centrifugal force. So there is, like I was saying, that there is a pull in centripetal acceleration wants to pull you in. Coriolis or centrifugal force wants to push you out.
Okay.
So the moment that I release, like as it's traveling, it stays in that angular motion, that circular motion, because it's attached to the string. But then once it detaches, it's moving at that velocity. So and then that same acceleration is gonna want to push it out.
Okay.
So, like saying, Centripetal acceleration again. AC, and then going out. Centripetal force. FC. AC equals centripetal acceleration. So then we talk about Coriolis, where Coriolis force.
Wait, so for the calculation, so I got the centripetal acceleration. Will we have to figure out the centrifugal acceleration, or is that just the opposite? It's the same thing.
Should be the opposite, yeah. Okay. It'll be the opposite. It's centripetal. So then say they gave it to me in revolutions per minute. Mm-hmm. 1 revolution equals 2 pi radians. So that's the 2 pi radians technically. They give it to me revolutions in minutes, revolution per minute, which RPM I was saying. So and then that's 2 pi radians over 1 revolution, and then 1 minute over 60 seconds. Mm-hmm. And then they might say, well, can you give me that? A lot of times they'll say, well, what is the force of gravity? Like, what's the difference? Or related, determine the ratio of this acceleration to that due to gravity. So and then it's a ratio to gravity. And that means that I'm definitely overcoming the force of gravity, right? Like, it's not, if I'm moving like this, I have a good amount of that gravity is able to keep it in its circular motion. But then as I pick up speed, gravity, I'm like overtaking a lot of that gravitational force. Okay. So, and then they say, well, how much of that is like stronger than G, basically. So that's what we get, the acceleration, centripetal acceleration over G. So that's what that was, or that's what that is when we're looking at it last class. So if I do 25.8 meters per second squared over G, 9.8 meters per second squared. So then I can say I'm overtaking gravity by 2.6. 2.6